aircraft testing and structures, aircraft structures and testing, and this will be presented by our CFT head Mrinal Manoj. And before that, I would request you all to unmute yourself unless asked to unmute, and close all your tabs so that there is no notification ringing and there is no disturbance for you, and you can concentrate on the session well. Now I'd like to hand over the session to Mrinal Manoj for the further proceedings.
So,
Mrinal, just a minute.
yeah,
Can you stop sharing your screen? We'll just click a snapshot and then after that we can continue.
sir. Yeah.
Okay, I request everyone to turn on their cam. Please, I don't have to say it again and again. Don't be shy, just turn it on.
Pratik, don't increase the tile layout, okay? Decrease it in such a way that all these guys come in the frame.
Yeah, right. Okay. Okay, I still see many of you guys haven't turned on your cam, so please turn it on. Everyone just turn it on, please. Okay, I'll click a picture.
Fine. So, shall we start?
Yeah, thank you guys. You can turn it off now.
So, am I audible?
Yes, Pranal, I can hear you.
Yeah.
Yes, sir.
Welcome everyone to the fourth session of aircraft structures and testing. So, in this session, we'll be going through the various stresses like that, when an aircraft is flying or when it's on the ground, like the various amount of stresses that, the aircraft will be facing. Then structural components of different sections of the airplane. In the first session, you came to know what an aircraft is. In the second session, you got to know about the principles. The third, you came to know about the CAD modeling. And now we bring each and every element together and we make an aircraft. So all the structures in making an aircraft, then, the suitable materials that will be we'll be using to build an aircraft, and some manufacturing and testing, procedures for aircrafts. So guys, what is the significance of structures in an aircraft? Anyone? You guys can speak up, it's fine.
It decides the lift and speed of the aircraft.
Okay, that's good. So basically we need, without structures, you can't basically make an aircraft as a whole. You need something to make out of an aircraft. So you need structures basically to make an aircraft. So moving on, whenever you make a vehicle or an aircraft, it'll have a lot of stresses on acting on the aircraft, whether it's on the air or on the ground. So we'll get familiarized with some of the stresses that acts on an aircraft. So first is tension. You guys are all familiar with tension. It's a pulling force basically. So that on an aircraft, the pulling force happens when, for example, your aircraft is towed. There's a tension on the body, especially when you tow the aircraft, there is a hook that tows the aircraft from the nose of the plane. So there's a bit of tension while you're pulling the aircraft. Then compression, so that's a pushing force. So you're crumbling a piece of paper, that's compression. Now compression is when an aircraft is landing, there's a huge amount of compressive force that acts on the aircraft, on the landing gear. Shear is something shear means the wings of the aircraft will be attached to the body, and there'll be rivets, or there'll be screws. So when plates move against each other due to the force, or from the friction of the air or acting on the planes, there'll be shear force acting on this screw. For example, if this is a screw, there'll be shear force acting here, and there might be a chance of failure that the rod might, the screw might just break. So that is shear. Now bending. Now, bending is basically a combination of two forces. Like whenever you bend something, like if it's bent if in this picture you can see, when you're bending something, you have tension on top. Like there is a pulling force on the top part, and you have a compression, or like there's a compressive force on the bottom half. And like along this curved line, there will be neither tension nor compression. And now this is called the neutral axis. This is called the neutral axis. So this is bending. Now, next one is torsion. Torsion is a fancy word, but it basically means twisting. So twisting is where, like, when the aircraft is flying in the air due to some small turbulences, the wings of the air, if you notice, like the wings of the plane will, like, it'll keep twisting. It, like, twist, like not so much, but it'll twist to a certain extent. So like this will give you a general idea of how the various stresses act on an aircraft. So you have your plane, like for example, this when the plane is flying, your upper skin will be in compression because the wings will bend upwards. So the upper skin will be in compression and your lower skin will be in tension. Then you have shear stress at the place where the wing and the wing is attached to the fuselage. Now, impact stress is something where, for example, the wind is coming at a certain velocity and it's hitting on this leading edge of the aircraft. So this is where the boundary layer separation, or like like in session 2, you had seen, like, the flow splits into two, and this is where the flow splitting happens. So over there, when the air hits on this edge, that's what impact stress means. Then bending and torsion over here is basically, this is significant when the aircraft is turning. So when the aircraft is turning this way, there is wind acting this side of the aircraft. So there'll be a twisting, or the plane will move towards the left, like when you're seeing it on the plane's perspective. But due to the air hitting on the tail, there'll be a twist or a motion towards the right. So there'll be bending and torsion for the vertical stabilizer. Then there is compression due to bending. This is basically when the aircraft is on the ground. So like you have a little bit of bending because of the weight of the aircraft. Now moving on. Now we'll come back to certain structures, like, how everything is built. So you can see over here, there are three main, ways of making a fuselage of an aircraft. First is the welded steel structure, which you can see here. Then there's the monocoque and the semi-monocoque. So the welded steel truss structure is the most basic structure, and it was one of the most commonly used structures in the early days of aviation. So it is constructed because you have these three main members here. You have one as the longeron, the diagonal web members, and the vertical web members. Now the longeron actually takes all the bending, the primary bending moment of, the primary bending force of, the aircraft or the fuselage is actually, taken up by the longeron. Then you have the vertical web members and the diagonal web members and the vertical web members, which reduces the extent of bending of the longeron. Like the longeron just alone cannot withstand the entire bending force. So it's actually distributed along these both. The forces are distributed along these both members, so that there is no case of failure. Now the monocoque is another type of, making the fuselage. Now over here you can see these three parts, that's formers, bulkheads, and stressed skin. Now imagine this as the end, the tail end of the fuselage of the aircraft. Now the bulkhead, basically this part, basically it is a member that gives partition to aircrafts. Like, if you can see, when you enter the aircraft, like the cockpit is divided from the rest of the cabin by, if you see the structure, it's somewhat like this. So this basically, it has dual function. One is that it also takes the stress from the skin of the aircraft, and it it evenly distributes it out, and it also gives like a structure to to make the entire aircraft. So that is the use of a bulkhead. Now a former is basically a lighter member of the bulkhead. So former is basically its primary concern is not to produce a partition in an aircraft, but rather take all the stresses from the skin and distribute it all along the aircraft. So, but the main disadvantage of this monocoque type of fuselage structure is that majority of the stress will be concentrated on the skin. So there's a huge downside of the skin tearing apart. So to overcome this, there is a new type of fuselage structure that is semi-monocoque. Now this is a very frequently used fuselage structure. Now over here, what they did is that they have the usual bulkhead, the formers, and the skin, and now they introduced a new component called stringers. Now stringers are, you had seen longeron on the welded steel strut structure. Now a thinner version of a longeron and a shorter version of a longeron is a stringer. Now what this stringer does is that instead of the skin having all the stress the skin transfers the stress onto these stringers, and these stringers transfer it onto these formers. So that way there's a transition of the stress, and like the magnitude or like the chances of failure can be reduced that way. Now the wing and empennage structures. Now when we come to the wing and empennage structures, there is a lot of structural components here. Now these over here are your control surfaces. So that's your aileron and flap. Then you have your root cord here, your wingtip here. Now, as you can see this green color long member. Now this long member is called a spar. Now a spar is the primary, stress absorbing member of the wing, and it basically deals with, most of it is bending moment, and there's also a little bit of twisting. Then there are, even your slats are also a type of control surface. It helps you to increase the lifting capability of your wing by, it comes out of the wing like this, and it actually increases your lifting capability of the wing. Then you have ribs. Now, the main function of the rib is basically, if you notice, the rib is in the shape of the airfoil. So it basically gives the shape of the wing. So like, you have these references. So a rib is basically a reference so that you get a uniform shape of the wing. And you have, again over here, you have stringers, which you had seen it in the fuselage. Now the stringers have kind of the same function here, but like there is a sheeting. Every airplane has a sheeting so that none of the internal surfaces are seen. So the stress caused by the air flowing over the sheeting is mainly transferred to these stringers, which these stringers end, or these stringers are connected to the ribs. So as you can see here, if I zoom in, the stringers are actually attached to the ribs. So the stress transformation or stress flow will be basically like, when it comes to skin friction, due to the skin stresses, it'll be transferred from the sheeting to the stringers, then to the ribs, and then it'll go to the spars. And if there are any twisting or there are any bending moments, it's primarily dealt with spars. So normally planes have one spar here and another spar in the front. That's actually kept, it's actually kept as a safety reason, because one spar sometimes just wouldn't cut it. It might actually break, the wings might actually break. So these are the that are involved in a wing and empennage, because empennage has the elevator and the vertical stabilizer, and they have the same or the similar configuration at the back too. Now, guys, this is a question for y'all. Why are these slots provided in the ribs? Even in this picture, you can see these holes here. Why are these slots provided here? And yeah, like why these provide? So can anyone open up?
Maybe because the force get distributed because of this.
That is actually, if you go into this, you can see that is one reason, because there is a method of cutting it. So this method, you can see this method of cutting, it's actually called milling of a rib. And this method is cut in a similar way so that there is, over here, you can see it's circular. Yeah, it is, yeah, a little more specific answer, to the point, a little more to the point. Why do you thing out from a
Aren't
surface?
we trying to, yeah, we are trying to reduce the weight, na? So
Yes,
obviously
that
we
is
need the least amount of material so to have the most support.
exactly. But can you cut this in any way possible, like however you wish to?
No, sir.
No, it
It
is
actually
No,
makes a basic shape of things.
Yeah,
we are
exactly. You
trying to make
can't
the trusses, right? So how,
exactly. Yeah. So there are various. It's basically called this procedure is called milling of an airfoil, and there are various. This is one type of milling. Like this method is one type. You can see the shape. This shape is one type. There is circular milling, as you can see here. You can read about milling. There are a lot of procedures, like there are a lot of methods for milling. So moving on. Now materials. Now how do we make aircrafts? So anybody can someone name some common materials used in aircrafts, like aircrafts?
RC ones I've heard styrofoam is majorly used.
Yes, yes, that's one. That's nice. And
And the real ones I have, if we are making, then aluminium is the
okay,
common
Magnesium,
that's
duralium.
sorry, I couldn't get you. Can you come
Real
again?
ones are made of magnesium, duralium.
I'm not really familiar with that. Like,
alloy of
Alu-
aluminium, zirconium.
Aluminium alloy.
yes, yeah, there is actually, it's actually made up of an aluminum alloy, that is aluminum 6061. And the 6061 is basically an alloy of aluminum, that's basically the major element in it. You have magnesium, silicon, and chromium, I guess. So these four, it's basically the sheeting you can see outside of the aircraft is basically this alloy called aluminum 601. So it is, the commercial aircrafts use it. Like any other materials, guys? Anything else that like anything other than
the
concentrating on the
plastic
metals?
I'm not
would
sure, but
be
maybe
used a lot.
carbon fibers.
Yes, carbon fiber. That's amazing. And anything else?
Plastic would be a good choice, a strong plastic.
Yeah, a strong. Yeah, they actually do use. You do use. Okay, now let's move on. Like we'll come to know about more of the materials. Now these are the materials. Like mostly, like this is in terms of aeromodeling only. So, but composites is, you can see it in both the commercial aircrafts and the RC aircrafts. So polymers. So anyone, like someone told it right in the questionnaire on top. This is styrofoam. Now styrofoam is an addition polymer, or styrofoam is a common name for polystyrene, which now styrofoam is very light. That is one of the the most common use of this material, and it is it's weather resistant. Like even if it's raining or whatever it may be, your flight will fly and nothing is going to happen. And it's one disadvantage is that it's not highly impact resistant, but it's impact resistant and light compared to others. And even Depron is also a commonly used polymer, but the problem is like Depron is too stiff. So due to this stiffness of Depron, like it's hard to form these wings and things like that, like of an model RC plane. So that's why we stick to styrofoam. Next one is composites. Anyone has any guesses on what type of wood this is? There's a particular type of wood, and it's very famous in the RC or the RC aircraft modeling industry. Anyone? Okay, so this is balsa wood. Now, balsa, I think you'll once, in this chapter, you'll kind of get to know, like balsa is one of the most one of the most used natural composites of used in aeromodeling. Now, why balsa? Because balsa has a very high impact resistance, and apart from other woods, it's around the third or the fourth lightest wood that is available on in the world. But the first, second, and third cannot be used because it's very fragile. So balsa is very flexible and it is highly impact resistant. And why balsa is used is because if you actually take the microstructure of balsa, okay, it's actually in the shape. Is one of the most stable structures that we know till now. So any impact or any type of stresses, the balsa can easily hold it up. So that is one of the most, and balsa is not very costly and it's easily available. So that is one of the most common reasons why people use balsa wood in modeling these aircrafts. Now, one more thing. In natural composites, in man-made composites. Now, any guesses on what this material is? Guys,
Carbon fiber.
it's black. Yes, exactly. It's carbon fiber. So this is a carbon fiber composite, and you all know why everybody uses carbon fiber, because it's very hard. I mean, it's very stiff and it's very hard, and it has 5 times the strength of the of normal steel, and it has a high strength ratio. So, and another man-made polymer that we use in aeromodeling is plywood. So plywood is also a very common type of composite that we use. Like, we use it to make the entire body of the aircraft. But carbon fiber has, like, in the competition basis, we have certain rules. So you cannot make an entire aircraft out of carbon fiber, and we would, like, there would be holes in our pockets. So carbon fiber is mainly used in specific parts. For example, you have these rods, or earlier I had mentioned spars. So spars and the landing gear part of RC model airplanes are mostly made up of carbon fiber. Then we'll get to manufacturing. Now you know how to make the structures. You have all your materials with you. Now there are various types of manufacturing. Now when you come to manufacturing, you have 2 common methods, that's and one is additive. Now over here, what you see is a laser cut CNC machine. So it's also called a laser cutting machine. So over here, what they do is, like, you have your material and you cut the shape from the material. So there is huge amount of wastage. That is one disadvantage of CNC. It's very fast, and you need a CNC machine to do this, and it is very precise as of now. So this is one of them, that there's a laser cutting machine that we often use, and you can see they're cutting an airfoil here. And anybody knows what's the full form of CNC? Anybody? You guys can speak up. Okay, like, when the questionnaire or the doubt session comes, till then I'll give you time. Like, think about this. What is the full form of CNC, and, like, come to it. Now, one is additive manufacturing. Now, additive manufacturing is a pretty new concept. Like, it's used to make small CNC machines are used to make big components. Like, it's used to make, the airfoils and the other part, like, the fuselage, the bulkheads and things like that. If you're making it with balsa or any other material, you can use CNC. Now, when you want some specific or small components, you go for additive manufacturing. Now, one popular method, as you can see over here, is 3D printing. Now, they use a lot of materials like ABS, and there are some that do PVC, and, like, there are a lot of 3D printing 3D printing materials that people use. Now like a new era has started, because, like, there's a lot of wastage in subtractive method of manufacturing. So additive manufacturing is used in metals right now. So additive manufacturing in commercial airplanes, like as you know, like in turbines, the turbines are the most hottest part of an aircraft. So inside the turbines, like your turbines has to be like very strong. So before they used to use titanium to make the turbine. Now also like they do use titanium, but they use another material called a nickel super alloy. It's something called a super alloy, and it's a combination of many elements. And nickel is one of the main components. And now it's still a huge area of research. So nickel super alloy is something that they used to make, the inner turbines of the jet engines. So now we get to aircraft testing. You have made your aircraft, now you are ready to fly it, but you've put in all your time and effort into it, and you just don't want your aircraft to crash. Like that is going to be bad. So before that, you do some testing. So these are some of the one of the main three ways of testing. One is CG balancing act. Another is to calculate your thrust to weight ratio, and the flight test. So as you can see here, this is CG balancing act. Like in session 2, if you guys remember, I had introduced neutral point and CG positioning. Now, CG positioning is very important when it comes to longitudinal stability. So longitudinal stability means the pitching up and down stability of the aircraft. Now you can see over here you have this wooden L-shaped structure, and this is balanced right here. Now what you do is that you have your components. So in the next session, you will come to know about your servos and many other electronics in the aircraft. So you cannot place them anywhere you want. So over here, the aim of this CG balancing act is that when you balance something, the aircraft has to be in a horizontal level. It should not be like up or down. It should be like in a horizontal line to the ground. So that is the main aim of CG balancing. Now, if your CG is too backwards, your plane will not be longitudinally stable. Like the pilot or the person who's driving the RC plane will have to keep putting inputting inputs so that the aircraft balances out itself. If your CG is too much in the front part of the aircraft, the aircraft will be very stable, or it's a term called becoming nose stiff. Now the thing about nose stiff is that when you land an aircraft, like the nose has to be upwards, but due to the nose being stiff, like your nose will never go upwards, and the aircraft won't generate enough drag, or it won't slow down so you can hit the runway, and your aircraft might crash. So you have to do your CG balancing act properly. Moving on, your thrust to weight ratio. Now over here, your thrust to weight ratio, this is to measure, as you can see, this is a BLDC motor or a brushless DC motor, and you'll get to know about that in the next session. And whenever the thrust to weight ratio is basically whenever you fly an aircraft, in most of these competitions, you'll have to carry a payload. You'll have to carry a payload. So with the payload, your plane will have to climb higher. So the rate of climbing is calculated by the thrust to weight ratio. The higher the thrust to weight ratio, the better it is, or the better capable the aircraft is to climb at a higher rate. So the thrust to weight ratio is basically your thrust generated by the motor divided by the weight of the entire aircraft. So in thrust to weight ratio, you have your motor here, and you can see this L-shaped structure here. Now this L-shaped structure is the distance from this point to the hinge is same as the distance from this point to the hinge. Now what we'll do is that we'll give maximum thrust, or like we'll put the motor at full throttle, And over here, you can see over here is a weighing balance. So when the propeller generates, when the propeller is on full throttle, it will push this lever downwards and exert a force on the weighing balance. So that way you will get the thrust part of the thrust to weight ratio, that you will get your MA, basically the weight acting, the force generated by this BLDC motor is exerted on this weighing balance, and you get a force. Now, what about this mg part? So basically, thrust to weight ratio means thrust generated by the motor divided by the weight of the aircraft. Now, the weight of the aircraft is calculated in a way. It's like you have a pulley and you have a rope here, and you tie your airplane upside down here. Now, this is one of the common ways of testing, like, your trainer aircrafts. And you have a plate over here. Now, as you're familiar with these circular weights of 1 kg, 2 kg that you find in your labs, we keep inserting these weights here such that they both are in the same equal, they both are in the equal, their bottom sides match, like they both are like equally balanced. So the weight that is put here will be the total weight of the aircraft. So then you can calculate your thrust to weight ratio. Now, flight test. Flight test is like you've done your CG balancing, you've done your thrust to weight ratio, and your flight test is basically you flying your aircraft. So there are some safety precautions you got to take while you're flying your aircraft. So the first point is that incorporate a buzzer. Now this buzzer is, as you can see, these pins. It will be attached inside. It will be attached to the battery. You will learn the various amounts of battery in the next section to like lipo and other things like that. So now what this beeper does is that if your battery is below a certain percentage, it will start beeping, so that while your aircraft is mid-flight, it will just not lose power and fall down. So this is the use of a buzzer. Now, propeller clearance from all sides. Whenever you're doing your first flight, no one should stand in front of the propeller or on either side of the propeller. You should always be behind the propeller. There are chances that the propeller might come out or things like that, and it doesn't, and you don't want to hurt anybody. So that is one. Then launch or take off against wind direction. You should always, launch, or you should always take off against the wind direction, because if your wind direction is either perpendicular to your plane, or like it's perpendicular or coming sidewise to the plane. If your plane is this way and your wind direction is like this, you will have, in session 2, there was a concept called side slip. Now you'll have the same thing called side slip acting on the aircraft, and it will be very hard to control the aircraft due to crosswinds. So always launch it against the wind direction. Now, this is how you do your first test flight. Like another major point is that whenever you're flying your aircraft and it's your first time flying your prototype aircraft, make sure that there is no one in the area that you're flying. You don't want the aircraft to fall on them. So the first is that you take off, then you climb to a certain altitude, then your wind direction is still this way. Okay, your wind direction is still this way. So you fly first, like facing the wind direction. Then you turn before the plane flies too far, so that you don't want to lose the connection, and reduce your power slightly, because you already have the added force or the acceleration due to the wind. So you don't want it to go faster than you can handle. So like reduce your power slightly, then let it fly downward, have a good hang of the aircraft, then turn again, and your final approach. Then flare is basically your nose would go up, like your landing stance. So your plane goes upwards and it gets to a very minimum speed, and like then you land. So This is your flight testing procedure.